Good afternoon. It's a pleasure to be here. Fort and I worked together, how many years ago was it now?
Oh, it's about 16 years ago.
16 years, yeah. So we miss you. We still miss you. So, okay, let me dive into this, this presentation here. Let me give you a quick outline of what we're going to talk about today. So first of all, Jacobs. Who is Jacobs? What is Jacobs? I'm going to throw out half a dozen example wind tunnels. I'll talk about Scania, then get into climatic testing, a facility that we built for Scania, and then we'll zoom in on a design task, one of many within a facility. The design task pertains to what we call bypass doors. I'll step through a few things there, and then at the very end open up for questions. If you have a question in the meantime, feel free to raise your hand, and I'll see if I can answer it on the spot. So Jacobs, show of hands, anybody heard of Jacobs? Okay, very good. So large engineering firm, tens of thousands of us worldwide, offices from Milan to Mumbai, everything from stadiums to bridges, pharmaceutical plants, petrochemical stuff. In Tullahoma, we have one of three offices for what we call a technology group. We started designing test facilities out of Tullahoma as a spin-off from Arnold Engineering Development Center. We then opened an office in Detroit, Michigan to cater to the big three, and more recently an office in Munich. That was a direct result of doing two wind tunnel designs for BMW. As far as wind tunnels go, there are all sizes and shapes. Any guesses on whose wind tunnel this is? Anybody? Looks pretty old, doesn't it? No guesses? First guys in flight. Yep, that's a replica of the Wright brothers wind tunnel. So as far as modern wind tunnels, what we build, we're doing a lot of adaptive wall and aeroacoustic. Altitude tunnels are unique. We're doing one right now for Ford in Europe. Basically, the whole tunnel fits inside a concrete pressure chamber, and we can take it up to the same altitude as Pikes Peak, so they can run their cars simulating, you know, the lower air densities at altitude. We're going to focus on climatics today, climatic tunnels. Special purpose, we're doing a tunnel right now for a West Coast university, and it is actually for bird flight testing. So they train the birds to fly in there, and it's pretty amazing. All righty, let's go through some examples here. I'm going to show two graphics first, just to kind of get those of you unfamiliar with wind tunnels up to speed. So we'll start at the test article. In this case, this is a VW Jetta. This is a design we're doing for Volkswagen right now. And starting there, the airflow goes down what we call a high-speed diffuser. We call this corner 1, corner 2. There's typically a catch screen on corner 2 for debris, FOD. Fan, this entire leg here we call the back leg. The flow comes around corner 3, goes into a heat exchanger. As you circulate the air, of course, it warms up. And so you're looking for consistent test conditions. So this is nothing but a huge radiator. You come through corner 4. You can see a little guy here for scale. After corner 4, we have what we call a stilling chamber with a honeycomb, some screens, a contraction, and a nozzle. So all of these components are pretty typical of a wind tunnel. This one's an open jet tunnel, and the car is on a turntable so you can yaw the vehicle. It's also on a moving ground plane so that your flow under the vehicle is accurate. Variation on this is a circuit that goes over the top. This is pretty typical of a climatic tunnel. So test article, corner 1, 2, your fan and your back leg over the top, corner 3 with a diagonal heat exchanger, and round through your contraction. All right. To get the vehicle in, the turning vanes in this corner spread apart. All right. Some real-world examples. This is one of the two tunnels we did for BMW, which allowed us to open our Munich office. That's a 60% M3 vehicle there. The wheels are not attached to the car. The wheels are totally supported off the arms. The car is supported off this strut and this hexapod. You can change the height of the vehicle, pitch it, roll it, and all the loads are measured. The aero loads on the body are measured through there. And you can see this is on a moving ground plane. This is a stainless steel belt, a millimeter thick. The belt speed reaches 300 kilometers an hour, so 180 miles an hour. And you can see the tire marks here for when they had a full-scale vehicle on a prior test. This is an adaptive wall wind tunnel in Japan. This was for Honda. And the walls here are all plastic. This is about 1 inch thick acrylic, so plexiglass. And the walls change shape. We have pressure sensors, basically static ports, all down the sides. And what we do is we check the pressure gradient down the length of the tunnel with no test article. When you put the test article in, you have blockage, right? So to simulate the free stream environment, you actually bulge the walls and the ceiling around the test article. This is something we patented. You can see also there's a scoop here on the floor. This sucks off the boundary layer, the slower flow. So all these tricks to, I wasn't supposed to do that. Okay. All right, this is a NASA Langley 14 by 22 wind tunnel. Our company built this probably a few decades before even I was born. It's an acoustic tunnel. You can see all the sound absorbing material, but we retrofitted this system overhead, and they wanted to do acoustic testing. Imagine an aircraft taking off. What's the noise footprint on the ground, right? So what's going on here is things are inverted. That disc you see up there represents the ground, and there are about 200 microphones in that thing. And we designed the system to move it around to upgrade this tunnel. And that little jet model actually had canisters about this big that burned Jet A to make the right amount of noise. So, all right. This is my favorite. Unfortunately, I can't show you a picture of the real thing, but I was fortunate enough to spend 2 months in Italy last summer. And the little red car there is probably a clue. All right. Okay, let me switch gears. Who has heard of Scania? Yeah? What products have you seen of Scania? Trucks? Yep. Okay. And the country they're from? Sweden. Very good. Have you been there? It's a nice country. A real nice country. Scania has been around for a while. The photo on the top left is a Scania vehicle from around 1910. Those are actually oil wells in Russia. And the gentleman in front of the car is one of the Nobel brothers. If you've heard of the Nobel Peace Prize, obviously they were into oil, into explosives. I think TNT might be a Nobel invention. The photo on the lower right, that is a boat with a Scania motor from around 1910, and the bus is from the early 30s, also a Scania bus. They're still making trucks today. These two are 100 years apart. I just think it's kind of neat that we've gone from a chain drive to differentials and a hand crank here to raise these jack screws, to hydraulics. So same stuff, but 100 years apart. I think it's pretty neat. I thought it's interesting how the pivot point here is not at the back of the vehicle. It's probably closer to the center of the load, so it can tip easier for hand cranking. All right. They also do marine engines. The red engines up there, there are 8 of them in a ferry, and then the one below is a Coast Guard type. They also do buses, anything from city buses to touring buses, and other stuff for engines. Any guesses on that cable car location? Where do you guys think that is? South Africa. Where in South Africa? Cape Town. Yeah, that's going up Table Mountain, and so there are Scania generators that run that thing. So if you haven't been there, it's absolutely a beautiful place. All right, so let's get to testing. Why does a manufacturer need to test their product? Anybody?
Run warranties.
Bingo, yeah, warranties are expensive, right? Okay. So you don't want to give your product to the consumer and have them be your beta tester unless they signed up for it. You had another comment? Absolutely. Yep. Yep. Testing is really, really important. You've got two images here, kind of extremes. It's also expensive to go out in the real world and test, right? If you're in Sweden and you want to do some desert testing, that's a pretty long haul. Probably the lower right photo is a bit more local. So let's talk about testing. If we bring all this stuff indoors, here's a Scania truck inside one of our test facilities. What you see on the right here is the control room. We've got artificial snow coming out of a nozzle. You can see the vehicle is chained down, load bars back here. Typically, our climatic tunnels can go from -40 to plus 60 degrees Celsius with solar simulation. -40 in Fahrenheit, anybody? -40 Celsius in Fahrenheit? Yep, good. All right, so here's the view from in the truck. You can see there are 3 horizontal wings here that are up in the contraction with spray nozzles. Those actually are parked outside, and 3 little doors open, and the 3 wings go in across the contraction, pin into the far wall, and then with the right temperature pressure combination, you can create snow. They're also used for rain. So here's the same test setup, and you can kind of see the facility here where the wheels are on some rollers that are part of a dyno below the floor. You can see all these T-slots for tying things down. There's an overhead crane for maintenance. You can see a bit of a solar panel here. We'll talk about that more. You can see some vanes here that direct the flow upwards to corner 2 and the fan, and there's the door to get in and out. Part of rain testing is soiling. So here's some fluid that has some dye added to it, some UV sensitive dye, so they can see what happens. You know, where does all the water run? And you can get a feel for the roller here, compression on the tire. And the view from the control room, you can see the truck here and the soiling test going on. All of this stuff here, as far as the control room screens and programming, we do that in-house, and a lot of my colleagues have expertise in controls and instrumentation. So it takes a big team. It takes a team to do this, a lot of disciplines that work together. And so let's just talk about the facility here. So just like in the first two renderings, we've got a circuit here with corner 1, corner 2, a fan over the top, and then down. So as I mentioned, the contraction here, we have 3 snow bars, and this all translates in, and then the flow comes out of the nozzle. Most of the European manufacturers and US manufacturers, the view from the control room seems to be flow going left to right, or they view the driver's door. In Asia, it's typically being the other way around. Okay. This is what that job site looked like. So we did enough design to be at this point. The building's not shown here. Typically, we team up with an architect. But start a construction in Sweden. What you don't see off to the left here is the rest of the Scania complex. It looks like we're out in the middle of nowhere, but there's actually a city here to the left. This is pretty typical of noontime in Sweden in February. And then, of course, the building goes up. You can see here, architectural cladding, the office and control room, and you can see the duct over the top here. So the fan would be right in that area right there. And then as the building goes along, I mentioned it takes a team. This is my dear friend Jürgen. He's out of our Munich office, and he's my structural counterpart. We shared an apartment there. My wife was able to visit a few times, and it was a good project. So let's talk, now that you've seen snow, rain, let's talk about how you'd test this indoors. What have we got going on here? So we've got incline, curves. Yeah, curves are kind of hard to test indoors. But really, we've got an incline. We may have temperature. We may have altitude, which could be a dedicated facility for altitude. But To test this indoors, here's some considerations. We've got the grade, so we want to load up the vehicle based on the grade and the weight. We want to adjust our airflow to match the vehicle speed. We've got solar issues, air temperature, altitude and noise. We could bring those in. I'd say altitude is going to be a special facility, but more and more, even your generic type climatic tunnels do have sound absorbing material. So let's jump to this situation. Here's a setup where we've got full solar going on. We've got load bars, so the dyno can load this thing up, and this thing is working just like it's climbing a hill. We also have vertical load. Take a look at these hydraulic actuators right here, and this spreader bar across the top. So that's pulling down on the chassis to load it up. But here's where things get a bit tricky, all right? You're running down the highway, and now suddenly you've got a steep grade. What happens to the truck? It slows down considerably, right? That engine is hot. You now have very little airflow impinging on the radiator. So basically, your forced convection has gone way down, all right? And how do you simulate that in a tunnel? You've got that fan overhead, and it's spinning, and it might be a fan that's 3, 4, 5 megawatts. Can you turn it off in a hurry? Takes a while, doesn't it? Sometimes a minute to spool down. But the truck can slow down a lot faster. And so we're talking about steep grade testing. Now, the counterpart is a city idle test. Let's say you're running through an interstate through town, take an off-ramp, and bingo, here's a red traffic light. The truck has all this built-up heat in the engine system, and now suddenly you're idling at a traffic light. How do you simulate that? What we do is the flow out of the nozzle, we have to somehow stop it and either turn off the flow or reroute it. So the question is, turn off or divert? Well, we've got to maintain control of the tunnel temperature. We can't stop the fan in a hurry, so we must maintain circulation of the air. So what we do is we divert the flow that normally comes out of the nozzle in front of this to the sides, okay? And this is where this bypass door system or bypass system comes in, and it's basically driven by these two tests. So let's talk about this door here. Let's say we do a door. It's got to close off the flow. We want to make sure it can handle the hot and the cold. We've got to make sure it's reliable. Depending on how we design the door, is it a guillotine door? What if it comes down on somebody? All right, let's say there's an operator in there. Do we decapitate them? Do we cut off their hand? I mean, there are all kinds of considerations. We've got safety concerns. So let me just see here what, okay. So I'm going to sketch here on the board in a second. So basically we have our contraction. I don't have the snow machine turned on here. But normally the flow is coming out of the nozzle, and we have these two enclosures on the side that divert flow around the edges. So let me just sketch something on the side here. So let's say we've got a contraction, and this is, tell you what, hang on. I was a Boy Scout. They had a motto. So let's say you've got a contraction, and you've got some nozzle section, and let's say your test article is down here somewhere. So what we want to do is somehow close off this flow, basically a big valve. Have you seen loading docks for big rigs, where a big rig backs up and you might have this fiber reinforced plastic roll-up door? So sometimes we do that where there'll be a motor here and a big roll-up drum, and that'll come down, all right? So what we decided to do for this case was instead to put two hinges here and basically divert these doors inward to a condition where they basically met up on center line, all right? And you can see the safety concern there. You've got these two big doors that meet and touch right in the middle. Kind of looks like a shear, doesn't it? Okay, so we'll get to that. And then on the outside of this, which is what you see there in gray, we basically had these enclosures on the side, and there's a grating here and a grating here. So by basically hinging these two doors in, we suddenly divert the flow around. Okay, so let's just talk about how we might do these doors. This area is hot and cold, right? Do we want to put our actuators in here? We could. We'd have to probably wrap heat trace around them, keep them alive, right? But if we could put whatever device is outside, that could save our controls guys some headache. So let's look at some possibilities here. Okay, so there's the structure. So basically, the vent is on that side, and the door is underneath here. And let me see if this. I should have a video. There should have been a video right there. It may be on the next slide. Okay. So the stick figure right there represents this guy. And what we elected to do was have an arm from here to no, I drew it backwards. I had a link and an arm, right? And when it was open, it would be basically in line. All right, so familiarity with 4-bar linkages? Okay, so basically we've got a 4-bar. Got a ground point here. This is your input link. Another ground point there, which is the hinge of the door. Okay. Examples of other 4-bars, Nelson, since you brought your bike in. Seat is ground, 2 links, and your pedal crank. So lots of examples out there of 4-bars. So, pardon? Yep. So, so basically we just put some equations down and then varied this link. This is MathCAD. There are all kinds of solvers out there. You could do this in Excel too. But basically we swept this thing, and let's see if this will play. All right. Okay, so you can see your input link, your coupler link, and the door is your output link. So this is what we've got going on, and the door meets in the middle, closing off the airflow. Now, what we did is we played around with all the numbers to optimize this, and by playing around with the kinematics, we made our colleagues who are on the control side, we made their life a little bit easier. So if you look at the kinematics here, we're pretty close to in line right here. So our starting forces are pretty low on the servo motor, and then the forces are highest on the servo motor about halfway through, and then as the linkage gets straight, our forces go low again, right? So there's actually another benefit. Let's say right there, let's say something in whatever's driving this outside of the enclosure, let's say something slips. Let's say a coupling on a servo motor to a gearbox slips or whatever. Can the doors go any further? So inherent safety benefit there. They can only go that far. And if the blue arm overshoots, the door starts to come back. All right, so a huge safety benefit there. So let's look at some of the things that we analyzed here. So as you know, with kinematics, you've got geometric inversions depending on which way things go, and you can put all this into simple equations. And so we ran several cases here. And you can see how the mechanical advantage starting out is really good. So this is when we first start to move the door from the flush position. And then as the door goes to the center, we're at maximum mechanical advantage. And as you'd expect, our servo loads and our loads through our arm are highest here. And I'm thinking this calculation package had about a dozen plots like this where we could just pick out what we needed. But you can see here the torque to that input arm starts out very low, rises and then drops down again. We couldn't make this perfectly bell-shaped. It just didn't quite work out. But as far as then, what do you do with these loads? You then take them and you want to look at all your components. So one of the simplest calculations is, okay, here's my linkage. I know it's a hollow tube. From our graphics, what's the maximum load? The loads, by the way, they had aerodynamic forces overlaid on that, not just accelerations, right? And it's just a simple matter of, okay, what's the cross-sectional area here, yield strength. Got a factor of safety of 15 on this guy. And we didn't have to look at buckling because the door's trying to swing open and it's therefore pulling this thing, all right? So there's no need to look at buckling. Component selection, sometimes it's just right out of a catalog, 50 kilonewton. There's your rod end bearing, okay? Catalogs are good, all right? The clevis where that rod end bearing fits, all right? Well, how about just a round end lug model from Peterson's, all right? And there's some charts that go with this where you can look up some stress concentrations. FE, I guess all of you have had a little bit of finite element analysis experience. Yeah, okay. So here's the arm, and really you just want to kind of optimize the arm since this is a custom part. So you can see here we've got a pretty consistent stress level down the whole arm. Obviously, if we were making 1,000 of these, we'd refine it further. We're just making 2. So you have to kind of evaluate, well, how much effort do you want to put in it? Is it going to fly? Is it not going to fly? All right. Again, some stuff right out of an engineering book. There's wonderful stuff in there that guys were using before FE was even available. So you've got a diameter that steps down to a smaller diameter. Well, we have 2 shoulders here. Let's look at some ratios of diameters. And we know from our MathCAD analysis what kind of torque we could expect on this. All right. Other catalog items. That arm, I'll show you some installation photos here. There's basically a plain bearing on this surface and this surface. So we select, again, a catalog item, just an IGUS plain bearing. And, we've got temperature here is a big deal. Tapered shaft lock, also. All of these screenshots are coming right out of a calc package. Okay, in this calculation package, I'm guessing it was about 40 pages. It basically documents everything we did. It allows our controls counterpart to then size and program a servo motor. It allows the administrative assistant who's putting together a folder for the maintenance staff at this facility to get cut sheets. So ultimately the client has a maintenance binder where when they need to maintain this once we're long gone, they can see what was selected and where the source is. All right, so it all ties together, servo motor selection. And before all of this gets built, we've got our calculations. One of our main milestones is the set of drawings to build this. All right, so this is the first sheet of the bypass door drawing set. Okay, so from this sheet, we would then have various components pointing to other drawings in this set. I think this was half a dozen drawings. The next sheet in this set was the actual door weldment. Okay, and then it would get into the more detailed stuff. There'd be installation instructions, vendor notes. All the items are ballooned. So this is a deliverable to the people building it, to our guys that are installing it, our guys that are checking it out, and long term for the client to then service their wind tunnel. All right. Look familiar? Those are your bypass enclosures on the side. Okay. So this was in, I want to say, Bulgaria. So our German subcontractor who did this farmed out this weldment to a supplier in Bulgaria. The labor was cheaper. All right. Here's a photograph from inside the nozzle looking downstream, so the doors are almost closed here. You can see the linkages are disconnected here. These 3 windows are where the snow beams come in. All right. And all right. You can see here that arm, that input arm, that was in the FE model. The IGUS plain bearings are right inside of this bearing support and inside of that one. You can see our rod ends, you can see the lugs. There is a tapered shaft connection here. This shaft goes all the way out, and I didn't show this, but there's a torsional load calculation on the shaft. There are brush seals here, and then above that, some more brush seals. So 2 levels of brush seal. And then on the outside of the enclosure, the whole thing gets sprayed with insulation, like a 2-part polyurethane. So the outside kind of looks like sprayed cement, like gunite. So this is before hooking it up. This is all acoustic treatment here. I mentioned that noise is a concern in modern facilities. And here's the completed hookup in the flush door position and a safety chain. Our thinking was, okay, what if one of these fasteners comes out, et cetera, even though that linkage goes straight? Worst case, what if this door swings and tries to go beyond position? It'll certainly bend some things, so there's a safety chain here. I'll talk more about some other safety stuff here in a second. So if we climb on top of this enclosure, and this is kind of during the construction phase, we're wearing hard hats and steel-toed boots and gloves, and Jacobs is very, very high on safety, which is a good thing. But you can see the servo motor still has to be installed here, and this is right out of some of our archive documentation for this project, where we did all the mechanical installation and checkout, and then prior to our controls guys coming in and putting the servo motor in and wiring up these over travel limit switches, this was basically an annotated photograph to help our controls guys. Okay? And there was basically a mirrored photo for the other side of the tunnel. All right? And all this area here, the structure, this all gets filled in with spray foam. What I didn't mention is you see how the structure is actually down here. And then this rises up, and the gearbox is mounted on this slightly elevated stand. Okay? And the reason is we want to have some material thickness there for the spray-on insulation. And you can barely see it, but it looks like a shim here. It's actually a phenolic spacer called micarta. So we're trying to put thermal breaks in there so that when the enclosure down below is frigid, that the cold temperature doesn't come up and gel the oil in here, et cetera. Okay? Alrighty. Okay. This is a screen image of a video of the actual installation. Before I run the video, I may have to actually pause the PowerPoint to pull a video, but I couldn't get it to embed for some reason. But let me point out a couple of things. So you can see a black line along here. That's a brush seal at the bottom of the door, right? Same thing along the top. There's a little box right here. This is a little heated enclosure, and inside it's got a laser pointer. And it puts down a line down the floor. That way they can line the vehicle up. All right. There's some lights on each side here which flash whenever the doors move. Camera. Grating here with the lock. But let's talk about those doors coming together. What happens if somebody's standing in here looking down into the contraction and those doors close? Bad day at the office, right? Okay. So we gave it some serious thought, and we found a safety measure there to make sure nobody gets their arm cut off. Any thoughts here? Any guesses? How do you make sure that these two doors don't come together? Don't come together when somebody's in there. Elevator has a proximity sensor. You're on the right track. Yeah. Any guesses? Some kind of sensor to detect if somebody's gone in there? Yeah, exactly. So we put some light, what's called an industrial light curtain, basically, if you can think of an electrical device, they come in various lengths, but basically one is an emitter and one is a receiver. You can't see the beams, they're not visible, but basically you see this vertical line right here? Okay, that is actually a plexiglass window. And behind that in the structure is an emitter on one side and a detector on the other side. And if somebody breaks that light curtain, then this door will stop functioning until there's a complete system reset on it. All right, so you can't have anybody in there. But this is a climatic tunnel, right? And this product is only good down to -20. So what do? Warm it up, exactly, right? So basically inside this structure there is an enclosure there, and in the bottom of it there's a little hole, and from below the floor we pump warm air in there to keep it alive. All right, so there are all these design considerations. Let me go ahead here and see how I think I just hit escape here, don't I? There we go. And video. Okay, I'll just pull it up here. Let's see if this thing will run. I've just got it on a side screen here. As soon as it starts running, it does. I'll drag it over onto the main screen. Okay, so here's a video of the real thing. If you watch closely, you can see how the door inherently is accelerating through the mid-range and decelerating at the start and end. You can also see the flashing lights there on each side. And my controls buddy Ron was videoing this, so I need to give him some grief about his shaky hand there. So, but you can see how the doors meet right on center. It's very fast. The client really liked it. It worked very, very well. So, at this point, I don't think so. I don't think so. I think this is when he got the controls kind of working, and he was happy, and he emailed a video back to the U.S. because I'd been supporting him by phone as far as, you know, here's the sequence of things to hook up. All right. You can see all of this wall finishing here. All of this is perforated acoustic skin, so it's all sound absorbing. Various alarms. There are all kinds of things in here from a safety perspective. Gas detection. Obviously, we don't want somebody entering the test cell if there are toxic fumes in there. There's some other interesting things. Is we can adjust the humidity in here from bone dry to like 99% Amazonia type levels. All right, and imagine a situation where the temperature is higher than your body temperature, and the humidity is in the 90s. You walk in, where does the moisture condense? If your body's colder than the ambient temperature, where does the moisture condense? Right on you, right? Condenses in your lungs. You can't stay in there long. It'll actually pool in your lungs and you won't know it. So there's some really strange situations you can develop, all right? So, also, you saw the snow images earlier. So it takes a while to get a whole tunnel down to that kind of temperature, right? Outside of the tunnel, there are what we call soak rooms, where the client will put a vehicle in there overnight and gradually get the vehicle to the desired temperature. It's a lot more expensive to put a warm vehicle in a tunnel, run the tunnel, and cool the vehicle. So they have these soak rooms to get the vehicle on condition. And if they're doing a -40 test, they've got a -40 vehicle that some technicians have to bring into the test section and chain it down and set it up. So there are all kinds of fun things with the job that I'm not sure everybody would be keen on doing. But it's pretty cool where you can be, you know, doing a summertime test and walk in and and have snow. Let me get back to this. Is that okay? So that's where we were. I'm actually going to stop at this point. Someday we may see something like that as a result of all these wind tunnel tests. But I'm happy to open up the floor to questions. If any of you are within a year or so of graduating and you want to email a resume, that is my supervisor's name. You're welcome to jot down his email address and send him a resume. Of course, I can take resumes here if you happen to have a printed one. Okay, very good. So let me just open it up to questions here. Wind tunnels, machine design, vehicle companies. Yes, sir.
With the fan, you said that it's a big fan, or it doesn't slow down very fast. Has variable geometry fins come into consideration?
Yep, absolutely. Those are there. Those are there. The issue is this: you've got this volume of air that is spinning around a closed loop. Okay, and if you look at the sizes we're dealing with, that is actually a substantial mass of air. All right, it takes a while to slow that air down.
And with the bypass
Mm-hmm.
going along the sides, I see there's no enclosure for that air to flow by it. So does that actually affect as well? Because you're going to have that ambient flow around that truck. Does that not? I would think that
Absolutely.
would correct.
Yes, I see where you're going. So here's the thing: is in an aerodynamic tunnel, having flow down the sides would be very much of a concern. Okay, what they're trying to do here for this test is they're really testing the heat exchanger, the radiator on the front of the vehicle, and the flow through the engine compartment. So it's a very specific test to say, okay, can our vehicle cooling system handle this, or does it boil over? Okay, so just getting the flow down the sides, it basically, you don't have that forced convection on the front where it would normally go. Okay, now I showed a picture of 3 buses there. Bus motors are generally in the back, right? So that's a bit of a trick for them. They can't really do that one as easily. All right. We did for this tunnel do some flow control devices. Imagine 2 huge wings that are stored on the side walls of the tunnel. When they put a bus in there, these wings lift up, say an inch and a half off the floor, and hinge in, and end up being right adjacent to the air intakes and the rear-mounted radiators on the buses. So there are all kinds of things. And again, do you want to have 100% simulation, or do you want to get very close? And what they often do, they'll take a vehicle out, instrument it, they'll run over some mountain pass, back and forth, data log everything, right? Then they bring those data log files home, and then they will set their chassis dyno to simulate all those hills, and they'll set the tunnel temperature, and they will run that same cycle over and over and over again and see where things fail, see where the truck has shortcomings. So it's a very, very good way to do things. Yes? Good question. So the question was duration of a project from design to completion. It's normally in years. If I look at some jobs, we've had marketing phases of 8 years where we chase a client for 8 years and finally they have the money in the piggy bank. But generally, assuming we've got the job, we'd go through a preliminary design, come up with our concepts, figure the design phase normally around a year. But you can often have the groundbreaking at the project site before. In other words, you can already have your basement levels and all that stabilized, and while they're already pouring concrete, you can be continuing into the detail design. So figure like the Scania project, that was about 3 years overall. And then sometimes, like Scania, they run their own facility. We have several clients where we do what's called design, build, and operate. If you're familiar with wind shear, it's a NASCAR wind tunnel. I suggest all of you look this up because they have a really good video of that moving belt ground plane, but it's windshear.com. We did the design of their facility, we built it, and the facility was intentionally designed to have more than one race car team there. It has 3 separate garage prep areas that are all secured from each other with swipe cards, and each team gets their allotted time in the test section, all right? And because the owner of the wind tunnel also has his own race car team, he needed somebody independent to run it. So there are Jacobs colleagues of mine that run this facility as the neutral entity. And whenever one team is done, basically that team receives all of their data, and then they verify that the facility's computers, the hard drives, are wiped clean. And it's in our best interest to make sure that nobody's test data are compromised, right? If there's any thought of their data being compromised, then they're not coming back, right? So it's a pretty good check and balance. So. Yes, sir.
What kind of diverse things can you test? Like, how diverse can you make a facility to test different things?
Good question. Yeah. So, you know, I've focused on wind tunnels here. The common theme in our business is testing, but it's not just facilities, it's also test machines. I'll give you some diverse examples. We did for Caterpillar heavy diesel engines, we did a design and built half a dozen machines that tested diesel fuel injectors. Right? And this was in a production environment. The injectors would come off the assembly line, and then they were put into a machine that simulated the engine head, and the injector was hooked up. It would fire, no combustion, but it would squirt the fuel, and we would measure the fuel quantities and all kinds of stuff. So, you know, but as far as think about the data acquisition side, you still have some kind of screen, an operator who's gathering data. So there's, you know, whether it's a wind tunnel with a big control room with 5 people in it, or a test stand, okay? Just down the road here, what used to be Saturn at Spring Hill, it's now GM Powertrain. We did a lot of assembly line type equipment. I remember doing a transmission test stand for them and various other items. We did for the US Navy, they have these, what's the name of that really large helicopter, like a Sea King or something? It has Stallion? Yes, thank you. They had a facility that would rebuild the transmissions for the helicopter, all right? And so here you've got this transmission that's rebuilt. They wanted to test it under load before putting it back into service, all right? So here you've got a transmission capable of, I don't remember the exact number, but let's say 2,000 horsepower going through it, okay? And how do you test it under load? So we designed and built a transmission test stand for them. And what was really unique, and I want you to think about this, all right, is instead of running 2,000 horsepower through it, we had a motor on there that was only strong enough to spin everything. Okay, so all the gears are turning. But between the input end and the output end, we actually coupled the output end back in, all right, through other gearboxes so that it was a closed loop transmission. And then partway in that drivetrain, we were able to add twist to the output shaft while it's spinning to simulate the torque, okay? So the test stand motor was only a fraction of the horsepower needed just to spin everything, all right? But think about that from a drivetrain design point of view.
I know a lot of you've got other places you got to be. I think Leo can hang around.
I can stick around if anybody wants to come up here and talk one-on-one. I'm more than happy to speak with you. So,
Great.
thanks.
This was wonderful.
Glad you liked it.
Thank you.
Thanks. Thanks. Thank you.